Dr. Kesavan, I think it's a right
Professor,
time to
shall we?
start.
Yeah. Okay.
Okay. Sure. Okay. So good afternoon to all of you. Welcome to the third lecture of today. And this lecture will be offered by Professor Phanikumar on solidification, microstructure, and defect formation during additive manufacturing. Just a brief about Professor Phanikumar. Professor Phanikumar got his BTech degree from Metallurgical Engineering from IIT Madras in the year 1996. Then he moved to IIC Bangalore and he got his PhD degree from Metallurgy Department. So then he moved to Germany, German Aerospace Center, where he got his postdoctoral research. Then he joined IIT Madras as assistant professor in the year 2005. So he spent from 2005, he spent at various levels from assistant professor, associate, and currently is serving as a professor. And professor is a well-known, eminent person in all across the country and international level in the area of solidification of metals and alloys. With this brief introduction, I welcome Professor Phanikumar to deliver his talk in this event. Over to you, Professor.
Yeah, thank you, Kesavan. Good afternoon, everybody. We have a long lecture today, so I would encourage time to time some of you to ask me questions so that it's interactive. It will also make it slightly easier to absorb as we go along. And I will have my talk in different parts depending upon how much time we have. I have covered all aspects of solidification microstructure as well as defect formation. So let us get some introduction. I don't have to introduce additive manufacturing to you because we are actually in the second day. So I suppose by now all will be familiar with that. So there is a, so are you able to see my screen change to the second slide?
Yes, sir, it has come.
Okay, okay. So, so you have the idea of laser deposition happening for repair applications as one of the early applications of additive manufacturing. It was almost 23 years back, to be precise. And so superalloys are very expensive, and therefore one was interested in ensuring that they are not wasted for small defects, and that's how it started. And as you could relate, the single crystal is able to grow all the way to the top, and that's how the single crystal was repaired. And it's not actually very easy. So today in 2021, through additive manufacturing, it is being attempted again, and there are some successes already. And so here is how it looks like. So the initial work was done by Wilfried Kurz in Germany, in Switzerland, and in EPFL. And so he published his paper 99. And from then onwards, people were very excited that you could grow microstructures of what you like using laser deposition. Today that is called as directed energy deposition. And so the enthusiasm started to pick up. Okay. And so if you were to make a bead using laser and chop it in two sections, so this is a transverse section, and you would see that the a single crystal, if you melt also, you would actually get different orientations of the growth. So on the left hand side, you see that the growth was happening laterally, and at the bottom it is vertically above. And it means that there is a specific preference with respect to the crystallographic orientations for growth. And this is something that we will actually delve bit deeper as we go along, and also see how it can be taken advantage of. And so today, if you look at certain alloys that are being pursued for additive manufacturing, so here is an example of 316L, which is one of the popular alloys. So you can see that there are many features of microstructure that are of interest. So you can see some cells or subgrains, and then you have got grain boundaries also. And you also have microstructural differences between grains, depending upon their orientation, the way we have sectioned. And the feature size is also very fine. You can see that it's about couple of microns only each of the cells. Partly this is responsible for the improved strength of additively manufactured components, but it's also important to know that the nature of defects or microstructural formations like grain boundaries and cell boundaries are still relevant within additive manufacturing as well. So for us to understand them is important to avoid any defects that will come. So I will actually discuss the defects as we go along. So then you would see that the entire metallurgy starts to becoming relevant when you go to some alloys. So here is another example of titanium 6 aluminum 4 vanadium, where you have multiple types of microstructures emerging within the build. So electron beam based directed energy build was done. And you see that at the bottom you have got some equiaxed grains, and then as it grows, you have got a columnar grains. And then there are some regions which have what is called a basket weave structure, typical of alpha beta titanium alloys. And as you can make out that there is a heterogeneity of microstructure in this particular alloy. And we have, depending upon our applications, specific preference for some of these microstructures. So if you see the columnar growth, the grain boundaries are vertical, which means that you may prefer them in applications where they are along the height of a blade, so that the stresses acting on a blade would not lead to any failure because there are no horizontal boundaries, it's only vertical boundaries. Similarly, if you take a component that is not subjected to a directional load, equiaxed grains are perhaps preferred because they have a lot of grain boundary area which can absorb the energy in propagation of any crack, and therefore they are fairly tough. And so one may prefer equiaxed microstructure in certain applications. And there are also applications where we want to very carefully ensure that the basket weave microstructure is aligned in such a way that it gives you good toughness. So we have different applications for different microstructures, but they can all occur in a single build if you are not careful. So understanding the microstructural evolution starting from the liquid all the way to the component is important if we want it to be successful build so that it's a near net component. Okay, so what are the kind of concepts that we learn and where are it will be useful? So one of the things that we need to understand is microsegregation and homogenization. That is, how do the elements segregate as the solidification is happening during the additive manufacturing? And then how do we remove those microsegregations by giving a homogenization heat treatment, that is holding the material at a high temperature so that the ups and downs in the compositions are flattened out. That's what is called homogenization. So we have to understand that very well, because if you don't do it carefully, you may have cracks. Okay, and we will talk about that. And we should also understand the precipitate nucleation, because we don't want to nucleate unwanted phases. For example, lavage phase in inconel alloys of nickel-based superalloys is a headache, and you would not like to have lavage phases when you build a component out of nickel-based superalloy powder. Sometimes a phase selection also will play a role. So, and you may want to also use the additive manufacturing for repair welding. So you can actually use these concepts for some kind of a financial benefit. And of course, this is actually at the core of the additive manufacturing. So we need to understand all these to go deeper into the use of additive manufacturing. And so solidification and defect formation, that becomes quite important. So what I do now is go on to open another PPT where I have the solidification concepts, and I do that to essentially illustrate some of the things, because I'm assuming that majority of the audience could be from mechanical engineering background. So can one of you respond if that is true? For example.
Yes, Professor.
Yes. Okay.
Yes.
So just 5-10 minutes of basic concepts of solidification may be useful for you, because that is happening. Okay. So now you see my presentation has changed to the solidification concepts, right?
Yes.
Okay. Yeah. So here is a video that shows you how an ingot is solidifying. So the heat is going away from the left, right, and bottom walls. So the solidification is happening from left, right, and bottom. And so this is a typically thought of as a tiny ingot in the case of additive manufacturing. So the liquid pool is like a tiny ingot. So solidification is happening in very similar to the ingot casting that is shown here. So the contrast of a bright region is solid and dark region is liquid is because of refractive index difference. And you see that the solid that is forming is actually moving around. It's not growing straight from the side or bottom. It is actually moving around. So there's some convection that is also playing a role. And these solid fractions are getting accumulated on the bottom, which is how the equiaxed microstructures are seen, because each of these solids particles are growing in the liquid equally in all directions, and then they are getting deposited at the bottom, and therefore you see that equiaxed zone can be explained. Now, as it is going towards finishing, there is some region of the liquid which doesn't fill up the void, and therefore you will have some shrinkage that is happening, and that is also known in the casting as a pipe defect, for example. And in the case of laser additive manufacturing, if the powder after melting doesn't fill the entire space, and you will have porosity. So the origin of porosity, you can also see here if it was incomplete melting, and that is one of the regimes that we will see. Okay, so you can think of the laser molten pool as a tiny ingot, and therefore learning about how ingot solidifies is going to be useful for us to explain. Now, many times we see microstructures in the additive manufacturing as a cellular appearance. That is, they appear like cells, tiny regions of uniform spacing. And the reason why it happens is that the solid front is moving in the liquid to grow, and it moves as a cellular front due to the solidification microstructure evolution caused by the so-called Mullin-Sekerka instability. Okay, so Mullin-Sekerka instability is basically, originally if it starts as a planar interface, due to fluctuations, thermal fluctuations, the interface will break, and therefore it will then form cells. The cells are very stable structures, and they can also have some orientation. So you can see there's a grain boundary between two cells because the orientation of the cells is different. And you see that there's a triple junction of the grain boundary here, and then there's a grain boundary that is growing this way. And this is the solid liquid front. This is all liquid, and this is all solid. Okay. Now, this is a video made of analogous material, polymer material, but the concepts that are seen are applicable, particularly in additive manufacturing, because there the motion of the heat source is fairly well known. And very often for superlight. Yes.
Sir.
Yeah,
Sir,
go ahead.
In the first slide, when we were seeing the ingot getting solidified,
yes,
there, but there we did not see such cellular growth.
Okay, good question. So this is at a large scale, and this is at a small scale. So to give you an analogy, when you look at the forest from aircraft, the forest appears like a patch of green region. And then when you descend into the forest, then you will see the trees and the branches, etc. So it's a matter of only the length scale. So this ingot is at a large scale. So in the order of, let us say, the size of the melt pool. And this is when you zoom in at a fine length scale, that is roughly 100th to 1000th of the size of the ingot. So it is a matter of length scale difference, because of which you did not see those patterns. So you have to zoom in basically. So the analogy of forest from the aircraft and forest as you are inside the forest is a very appropriate one. So that is the length scale difference that becomes evident.
Okay, okay. So there is another question.
Sure.
In the ingot solidification part, when it was starting to solidify, we saw that the particles were jumping off from their position and were getting at the bottom position.
Yes.
So can we predict before and from where the particles will get solidified and come to the bottom?
Yes, it is possible. So this motion of the liquid, this portion of liquid is predominantly in the case of ingot casting due to what is called buoyancy convection. And in the case of laser molten pool, such as in additive manufacturing, it will be predominantly due to Marangoni convection. So Marangoni convection is surface tension driven convection. So therefore here, if the laser is heated here and this is the melt pool, the temperature is high here and it's low here. And that difference is what is going to cause a surface tension driven flow called as Marangoni convection. And today we can simulate those convective patterns, and we can also predict how the solid is going to detach and do its circular motion inside the pool. And this is actually a very well established topic. So there is a paper of mine, first author is Mohan Raj, 2001. You can have a look at it. And then in the recent past, Arvind Kumar from IIT Kanpur, about 7 or 8 years back, his work also showed the same kind of appearances in simulation. So maybe I can just conclude saying that it is possible to simulate those phenomena quite accurately today. But
Okay,
what I am showing you is experimental, so that you are getting familiarized with the physical phenomena. Yeah. Okay, so when you zoom into the solidification front a bit closer, so you will actually see some tree-like appearances, which are also called as dendrites. And particularly nickel-based superalloys are very commonly found in the dendritic pattern. And the reason why the dendrite pattern comes is because of anisotropy of its growth and surface tension. And something that I want you to pay attention is that there's a latent heat released by the growing solid, because of which the side arms cannot grow, and elsewhere it will grow. So wherever the interaction between the solids happen, there is a latent heat released and the side arms don't grow. So a lot of patterns that are growing in the solidification can be understood once we know how these interaction happens due to release of heat during the solidification pattern formation. Now, what is it that is in between the trees? It is basically the liquid which is yet to finish solidification, and that is enriched with solute. What we mean by that, in the case of superalloys, it will be enriched with aluminum or titanium or niobium elements. So therefore, they actually lead to the segregation patterns, which if you etch, you can make out these dendritic appearances. So one can etch and look at the microstructures to see these patterns. And the intermediate liquid, dendrite liquid, actually will solidify and lead to the full solidification. And sometimes if the liquid was not enough, it cannot come in. Then you see a defect called cracking. Okay, hot cracking will occur. Okay, so we will come to that. Now, how does this actually the pattern formation happen during solidification? Here is a video that you can see that there is a grain of solid and it is growing. And as it grows, you can start seeing that the dendrites are forming. And like a tree, they are all growing, and there's a grain boundary also that is actually forming here. So this is a grain boundary. Okay, and these are all parallel dendrites that are growing, and in between them is the interdendritic liquid, which after finishing the solidification will merge. Okay, now the reason why the planar front initially became cellular and then dendritic is because of the instability I mentioned to you, which is caused by the segregation of elements. It's called the Mullin-Sekerka instability criterion. Okay, of course, the starting point of it is so-called solutal segregation or constitutional supercooling. But Mullin-Sekerka instability is a better way of calling it, because in the laser additive manufacturing, the extreme speeds will play a role, and therefore Mullin-Sekerka is a better way of referring to that. Now, when you wait for the solidification to finish, you will see that the interdendritic region will start to basically merge with the rest of the solid, and therefore these patterns which are actually seen here, they will start to disappear, because now the liquid is actually finishing off its solidification, and you start seeing that at some point it starts to become just a few dots of interdendritic liquid, and they will also start finishing off the solidification, and eventually you will see just no contrast because it is all fully solid. Okay, so this is how solidification happens in life, in reality, and the original regions of liquid are available for us to know because the segregation has happened, and therefore one can go and etch and find out where they are. So what happens as you increase the undercooling or increase the solutal concentration or increase the driving force, what happens is that the microstructure will start to change from planar to cellular to dendritic and equiaxed. So we are very interested in these transitions because if you want to print through additive manufacturing, if you want to make a single crystal, we must have our parameters such that planar growth is actually encouraged. Okay. And if you are interested in a microstructure that is resilient to crack propagation, it should be very tough. Then you may want to encourage equiaxed growth. So understanding these transitions help us in determining the conditions under which such microstructures will form. So that transition from planar to cellular is something that can be seen in metallic materials using synchrotron. And this is a video that shows you that the planar growth of grains can actually become cellular, and then those cells can actually become dendrites. So this is a live demonstration of how the transition happens. And this is actually what is happening in additive manufacturing when you are moving a laser, except that it is actually happening very fast and at a very small scale. But the physics is exactly the same. So this is a criterion I was talking about, the solute undercooling criterion or constitutional supercooling criterion, which tells you when does this breakage happen. And in the case of additive manufacturing, the velocity is known and the partition coefficient of the material is known. The liquid slope is known, concentration of the liquid is known, and therefore you can actually predict what conditions will give you the cellular formation. And you would see that you are actually in the regime where cells and dendrites are more stable for most of the additive manufacturing regimes. So this is how the plot would look like. If you increase the growth rate for a fixed temperature gradient, you will see that it would lead to planar to cellular. Or if you are actually having the constant growth rate, but increase the gradient, you can actually revert back to planar. So you have a way by which you can change over from one zone to another zone. And that is a play that we would like to use in additive manufacturing to get either a single crystal or a very equiaxed fine microstructure. Now, the equiaxed microstructure formation is evident here. Whenever the undercooling or driving force is available in front of the liquid, what happens is that instead of these grains, dendrites growing, you will have new grains nucleating in the front. So equiaxed microstructure can form. So I will repeat this again. So because this is quite a very important phenomenon, you can see that in the liquid, the solid is nucleating. And these are the equiaxed grains that are nucleating because there is enough driving force for that to happen. Okay, so that is also possible in additive manufacturing. If you go slow enough, you may have equiaxed growth that can take place. And here is again one more such illustration to show you how the dendritic growth is taking place. And so we would like to be able to switch between these modes by the change of process conditions as we do. Here is a place where equiaxed growth is also recorded. Okay, so this is what I'm showing you is a synchrotron visualization of aluminum alloy. So the so-called equiaxed microstructure formation is something that you are seeing with your eyes, except that it is enlarged and shown to you. But in the case of real additive manufacturing, it is all happening at a scale that is less than 1 millimeter for the entire zone that we are seeing.
Sir.
Yeah.
Yeah, sorry to interrupt, sir. Actually,
Go ahead.
there is, yeah, so the microstructure you have shown is just for the first layer or?
Yeah, so I will as we go along in some slides, I will show you exactly which part of the laser molten pool is like that. So it is actually a microstructure that is there behind the laser. And if you section it longitudinally, you can actually see these patterns quite clearly in any laser additively manufactured component. So if you know which way the laser is moving, then you can actually slice the bead, one single bead or one single track. If you slice, you can actually identify these zones. And in the case of multi-layer deposits, which are full component deposits, you can at least see the shape of the pools. And within the pool, you will see the growth happening laterally. And so you can actually relate the microstructures with what I have shown you.
Okay. Thank you.
Okay. Yeah. So now what happens is that these microstructural formations can also be suppressed, and that happens thanks to the surface tension effect. And that is where the Mullins-Ecker criterion tells you about the absolute stability. So what it tells you is that if your growth rate is very fast, then you can actually get an absolute stable growth, which means that there are no dendrites, there are no cells, the grains are growing as it is, and you get the same grain structure as what is in the base plate. So if you take a single crystal base plate, you can have a single crystal growth, but for that, what conditions are required is known here. You should have a high growth rate and preferably also high gradient, so that you are staying away from this pyramid of microstructural formation. So which means that you must identify what is this value. So therefore you can operate it for getting single crystal during printing. Okay, so that's why we have to understand this in order to take advantage of this knowledge. Okay, so today you don't need to worry about this, because today there are softwares available. So computational thermodynamics, which is giving a very nice way of understanding, is available today. At the click of a button, you can actually simulate these microstructures and look at how these changes. So you have a software tools that are available to do various aspects of what I have shown you. Specifically for microstructure is this Microsoftware, which actually uses the so-called CalFAD approach to represent the driving forces for the microstructural formation. And it uses the databases from thermocalc, which are essentially encrypted databases of Redlich-Kister polynomials. And for alloys like aluminum alloys, steels, nickel-based alloys, and so on, you don't need to now worry about what microstructure will come. You can actually predict it because they are all simulatable. And I will show you some examples from our own group also. So today, as you look at the various stages of alloy development, like casting or printing or porosity, eutectic phases, precipitation, all kinds of things are now possible to be captured by simulation. And the software we are talking about, Microsoftware, it talks to the thermocalc and it takes into account the actual alloy information and gives you the parameters such as the driving force, chemical potential, Gibbs energy differences, compositions, and so on, or properties like heat capacity and so on. And therefore, it will actually be able to simulate the microstructure. Okay, so that is a capability today. So by understanding the microstructural aspects, we are not necessarily going to an empirical approach, but there are tools available which allow us to even simulate and play with them to optimize a particular microstructure to be obtained by a particular 3D printing exercise. Okay, so I will now go further to show you some developments in that. Yeah, go ahead. Yeah.
Sir, in the previous presentation, could you open that for a while?
Yeah, I can open it again. Don't worry. Yeah. Yeah. So where do you want me to go?
Sir, sir, the previous two pages earlier. Yes, sir. Sir,
This
two
one?
pages later. No, sir. The next one. So
Here?
the previous one. Sir, sir, the previous one.
This one? Or this one?
This one, sir. This one.
Okay. 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 Okay.
Sir, if we play this, the thing.
Yeah. So what you are seeing, I will tell you. You are actually initially growing slowly, then you have increased the speed. So what happened is that initially it was growing as dendritic, but later on the equiaxed growth has taken over. So this transition is called as columnar to equiaxed transition. Okay, so this transition happens in ingots, it happens in welding, it happens in additive manufacturing also.
Sir, if we start it from the beginning, there is a point like these grain structures are falling down.
Yes.
Sir, please play it again.
Yeah, they are falling off. Yes.
Yes.
Yes. Yes.
Yes, sir. Sir, but some of them get stuck there. So there must be some opposing force against gravity, right? So
so maybe I should tell you how this is done. So this particular visualization was done between two graphite sheets and a thin 150 micron aluminum alloy sheet kept between two graphite sheets, and then they were held by a boron nitride capsule around it, and then kept in the path of a synchrotron radiation. So what happens is that sometimes the grains are stuck to the wall, and some of them are nucleated between the walls, and therefore they are free, and therefore they fall in the liquid. So if they are not falling, it is not because there is an opposing force. They are just nucleated on the wall, and therefore they are stuck on the wall. That's all.
Okay.
Okay, that's the only reason. Yeah. Okay. Yeah.
Sir, is that mode of solidification possible in pure metals also?
So the dendrite formation is possible in pure metals for a particular situation called as undercooled melts. Okay. Only difference is that it won't matter to us, because even if that pure metal is growing as a dendrite, ultimately the region which is between the dendrites and in the dendrite, it's all the same metal. There is no difference in the composition, and therefore it doesn't matter to us. Okay, so that's why we don't need to talk about it. Okay, but the concept of dendrite formation is very much applicable even for pure metals, but only in undercooled melts. Okay, it will not take place in additive manufacturing, because in additive manufacturing, the thermal undercooling is not available. I'm coming to that in a moment. And therefore, in additive manufacturing, you don't have dendrites of pure metal, but in other experiments such as casting, for example, or droplet solidification during powder fabrication, etc., surely you will have dendrite formation of pure metals also. But it doesn't matter to us, because dendrite and interdendritic regions are identical, so it doesn't matter to us.
Okay, thank you, sir.
Okay, yeah. So shall I move on to the segregation things? Okay, so now, because we are now familiar with the what is solidification, how the microstructures look like, etc., so I can now go and show you the segregation patterns and how we simulate to understand that. Okay, so this is a work from my student Mohan, and he has done both experimental as well as simulation. Okay, so you see here, where are we, at what scale are we looking at? So we are looking at a scale where you have got a laser that is melting the powder and making the 3D component layer by layer. And if you zoom into that region where it is getting solidified, you see that this white dotted line is the molten pool, and the re-emitting region is having a temperature gradient. And if you look at that small box, that is where the solidification is happening in normal to the interface, and the solidification is happening in the mode, namely the cellular mode. Okay, so that is the scale we are talking about. We are talking about a micro scale compared to the component. Okay, so the ideas of the solidification are applicable for continuous casting also, and also for ingot casting and welding. And what happens in laser additive manufacturing is particularly of interest for us in this workshop, but it's the same concepts, except that the length scale and time scales are much smaller. So that's the only difference. Okay, now these are some of the equations that we solve to understand microstructure evolution. So some of you who are interested in doing a mathematical way of understanding can reach out to me. Ours is one of the few groups in the country who do this phase field modeling, and we have released our programs open source. And so if you go and search for microsim on GitHub, you will see the programs which will simulate what I'm going to show you now. And therefore, that is something that you can also do if you are interested. Now, these solidification models have some parameters that are important for an additive manufacturing engineer to know. For example, the thermal field is modeled in this manner, where the temperature gradient is given here and the velocity of the laser heat source is given, which means that when you change the velocity or of the laser, or when you change the temperature gradient by giving a preheat to the powder bed, then surely you are changing the thermal field of this during the solidification. And once you change the thermal field, what happens is that it will go and affect the driving force, and therefore it will also affect the microstructural formation. So that we will see here. So earlier I have shown you the dendrite formation. So here is a computational dendrite. So this is done in the computer, and it is done to show you the segregation of elements like niobium or chromium in a superalloy. So the enrichment of niobium is shown here. Wherever it is red, there is more niobium. Wherever it is green, that is the average value. So you can make out that niobium is segregated between the dendrites. Now that is something that is important, because excess niobium can lead to lavage phase, which is bad news. So ability to simulate the segregation is something important. Now in additive manufacturing, you can do that. The challenge that was in the past was that there were many elements. You can make out that a superalloy will have so many elements. So simulating microstructure evolution with all the elements is a bit costly. But today it's possible. So we have taken up that to show you. So 7 elements can be considered, and Mohan has done his simulations on a multi-component alloy. So you can simulate the microstructure evolution in the computer at different processing conditions, like the temperature gradient, 10 to the power of 5 Kelvin per meter, 10 to the power of 6 Kelvin per meter. So think of it like this. If you have a preheat for the powder bed, the temperature gradient can be reduced. And if you do not have a preheat, then the temperature gradient is high. So you can think of this microstructural difference as what happens when you have preheat and what happens when you don't have a preheat, something like that. Okay. So the temperature gradient actually makes a big difference to the microstructural evolution. You can make out that at lower gradients you have dendrite formation, whereas at higher gradients you have only cellular formation. And therefore the spectrum of compositions explored also is different. You see that the segregations are much more severe when you have got the interlocked regions in the lower gradient, but in higher gradient, you do not have that problem. There's hardly any region that is red in this domain, which means that the segregations are not such a big problem. So that is a very clear indication that by playing with the gradient, you can actually obtain the segregations under control. So that's a first hint that we can get. Okay, and then we can also do a time evolution of what's happening because this is done in a computer. So to visualize what is happening during solidification at a small scale, you can actually do it in the computer. And so as the time increases, you see that the pattern formation is changing and for a particular gradient and velocity. So which means that the time evolution of a pattern formation can also be understood, which then can lead to us explaining what happens at the beginning and at the end of a track, for example. Okay. Now we also benchmark these simulations. So here is an experimental specimen. The tracks are here, the laser tracks, the cellular patterns of the laser track is here. So when you take a line and then do the compositional analysis, you see ups and downs of the composition like chromium content or niobium content. And the simulation is shown here in bottom figures, showing you that we can reproduce those ups and downs of the compositions quite well in terms of the wavelength of the composition variation as well as the amplitude of the composition variation. If you calibrate it for one sample, you can reproduce it for many samples. Okay, so this microstructural variation is something that we can simulate and therefore also control, because we can always simulate for conditions and then go on to print it such that we have the segregations as we want. Okay, now what is the use of doing this? The advantage of doing simulations is that you can actually go on to find out whether we can calibrate some of the known models of the spacings of the printed microstructures. So the spacings are lower means higher strength. Okay, so some such correlations we can calibrate, and thereby we can actually predict what is the way the spacings are changing when you change the process condition. Okay. So if you are changing the temperature gradient or if you are changing the velocity of the laser, then how does the primary dendrite arm spacing change? So that variation can be calculated based upon some simulations that you have done, and later you can actually use it for extrapolation. So that is the idea. Now, if you change the cooling rate also, these things will change, which means that if you play with, let us say, a helium, removing the heat from the laser printed component compared to, let us say, argon, then cooling rate is more with helium. And how does that affect the microstructure is something that you can predict by doing these simulations. So the primary dendrite arm spacing, for example, if you look at the red square versus stars, red square shows you that at a lower gradient you are actually lower here, and at higher gradient you are up here. So that means that for a given cooling rate, you can actually have a primary dendrite arm spacing increasing if you have got a higher gradient, or if you keep the horizontally, you can see that a higher cooling rate would actually be corresponding to a higher gradient for the same microstructure. Okay, so we will be able to understand the microstructure at every aspect of it, which is experimentally not possible. For example, what is the driving force at the tip of a dendrite? What is the undercooling that we are facing, and what is the temperature of the tip, etc. All of that can be now calculated, because once you have a model that is calibrated, we can actually do many of these calculations, which are not possible experimentally. Now, experimentally measuring the compositions also is available, but it's not possible to locate it everywhere, because the electron beam, which calculates the composition in an SEM, has a particular volume from which the composition is being measured. So if you want to make a composition map, etc., it's very painful, and you can only do it in 2D. So if you want to 3D how the compositional variation is happening, phase field simulations can give you. So here is an example of the chromium composition contours and the niobium composition contours in a 3-dimensional representation that is entirely possible. And you can then look at them to see how the islands of these compositional contours actually lead to some kind of a lock-in of the phase formations, which we related to, let us say, Navier phase formation at such locations when the chromium and the niobium content is high. Now, that's a clue that we can use these simulations to start predicting what is the phase formation. So we will do that. Okay, so we have validated these, and we will try to do that. So we refer to the so-called thermocalc-Scheil calculation, and as a function of temperature gradient and velocity, we go on to ask what would be the fraction of Lave's phase formation and what would be the fraction of delta phase formation in supernoise. Now that actually shows you that there is some processing conditions where it is very high, and certain other processing conditions where it is very low or tolerable. So which means that you can tune the velocity of the heat source or the temperature gradient, which is via the powder bed heating, preheating of the powder bed. You can actually achieve the fraction of the detrimental phase to be under control. Now that's a very powerful idea. So Mohan's work has shown that there's a relation between the processing conditions and the detrimental phases that may form in the additive manufacturing scenario. So the gradient values we have explored are relevant for additive manufacturing. Okay, and we can also then go on to predict the kinetics of phase formation, because these can be calculated. And when we do that, we are able to show that certain phase formations have a fairly leftward curve, which means that their probability of formation is high. Okay, so those are the kinetics we can do. Now we also can do bicrystal simulations to show how the space between two grains helps the liquid be present to fill the space and lead to prevention of crack or not, etc. So all those things can be done. So here is an example to show you that when there are grains that are very small misorientation, it allows for the liquid to be present all through. Whereas if you have a high misorientation between grains, then the liquid is present only a small region between them. So it is not having access to the rest of the liquid away, which means that when this region solidifies, it can leave some void, which can lead to basically a crack. Okay, so that kind of a indirect estimate on the effect of grain misorientations on crack formation during the solidification can also be thought of. Is crack formation a big deal? Of course. Those who are practicing additive manufacturing know that when they go to certain alloys, they simply cannot make the cracks disappear, and that is where we need to understand that quite well. We can also do for not only 2 grains, but for multiple grains to understand how the segregation happens and how the grain boundaries are actually locations of slightly higher segregation and so on. Okay, and of course, these are also benchmarked with respect to experiments. So we have to, of course, thank our colleagues for their help in doing these simulations. So I stop here and see if you have any questions on this aspect of microstructure formation before I move on to the remaining aspects.
Good afternoon, sir.
Yeah, proceed. Yeah.
Sir, this is Pramod from IIT Palakkad. Sir, in these aspects, sir, when you show these simulations, sir, but when we are doing the actual experiments, we generally play with process parameters like laser power, scan speed, hatch spacing, those. So, sir, how is it that we can correlate those process parameters that is an experiment with these simulation parameters? Like, so generally, what is the
so there are 2 ways. If you are looking at only the gross estimates, like what would be the porosity or what is the susceptibility to cracking, etc. Then there are some non-dimensional numbers that are defined. We will come to that in a moment. But if your idea is to understand the microstructural evolution, then you have to do it in 2 stages. Okay, you have to do first a first simulation with the laser heat source, its motion, and the laser melt pool formation, etc. as a thermal simulation you should do. From the thermal simulation, you should extract the cooling rate and gradient. And using those as the input conditions, then we do the microstructural simulation. Okay, so that approach of doing multi-scale simulation is something that I will be presenting in the end. We call it as ICME approach, so integrated computational materials engineering approach. So that is now today quite well established in our group. So we know which simulations to do at what scale, so that you can get the information correlated quite well. And there are tools available that we can share with you to do it, for you also. Okay, so it's not very difficult, quite well established tools.
Thank you, sir. Like my question was just in context with, like, if I'm trying to develop texture control in using additive manufacturing.
Yes.
So in that aspect, so this is the way I.
Yes. You should do for texture control. Actually, there will be 3 models available. 3 models because you need the system scale model for the thermal field evolution. You would also need a grain structure evolution with the orientation information that is being captured. And you also need at the microstructural scale for segregation, because the segregation is relating to the interfacial energy, and interfacial energy plays a role in the grain selection, which leads to texture basically. So the 3 levels that are available, and my student Hariharan is working on that topic, not specifically texture control, but his work has those elements in it. So I'll be happy to put you across with him, so he can tell you which tools he is using, and therefore you can also then try the same. The tools are available. Yeah, tools are available. Okay, so let's move forward now. So we have got porosity now. We just mentioned, so I will talk about porosity. Okay, so this is about Hariharan's work. He is a joint student with Professor B.S. Murthy and myself, and some ideas of porosity formation as a defect formation I want to show you. So this is something that in the physics of the additive manufacturing, laser powder bed fusion, for example, you are already familiar how the laser molten pool is moving, and to the when the scanning direction is to the right, and then as it is moving, then you see that this is a region where the solidification is happening, and you see that the various phenomena are taking place, various defects are possible, etc. Okay, now there are two. If you see porosity in additive manufactured component, it might have had basically 2 origins. The first origin is because of keyhole. So the keyhole idea, I have actually described the concept of keyhole formation in high energy beams in my NPTEL lecture on YouTube. So if you search for NPTEL lectures with my name, you will see one of those. I have explained the keyhole formation, the vapor formation, etc. Now here I would just briefly tell you that when a very high power laser is incident on a metallic material, and if the temperature is increased to the extent that a small amount of vapor is formed, then that vapor will absorb the laser heat completely. Suddenly the efficiency of absorption will go from 10-15% to 100%, and therefore the laser will penetrate much deeper, and it will form a vapor column. And if the vapor column doesn't move in a steady manner through the powder bed, then what happens is that some of that will be left behind without a closure of the void, and then you start seeing the keyhole induced porosity. So which means that it is a problem caused because your laser heat intensity is slightly on the higher side. Typically, if you increase the diameter of the laser beam, this problem will go away. Okay, so if you have a problem with keyhole porosity, if you increase the diameter of the laser beam, then this problem will go away because it will prevent the formation of keyhole basically. Now there is another porosity formation which is quite difficult to remove with respect to your laser characteristics, and that is because of gas induced porosity. That is, you know that the materials which are made using the powder formation, they may actually absorb the gaseous substances, like for example, you may have the gas that is dissolved, particularly hydrogen. If it was there, it will be dissolved in the powder. And when you solidify, because the surface area has been suddenly reduced, a lot of powder surface area is reduced, then that gas has to be sort of escaping away. And if it doesn't happen to escape, then they will actually coalesce and lead to some gas-induced porosity. The gas-induced porosity is difficult to eliminate using the powder characteristic, laser characteristics, because it is actually coming with a contribution from the powder consumable. So it's a consumable problem basically. So as you can see that there is a way by which we can understand defect formation in the additive manufacturing. And so lack of fusion and keyhole both will give you porosity, but they're actually on the other sides, each different sides of the power spectrum. So you have very high power, you have got keyhole porosity. You have low power, so low that actually the velocity is too fast that it doesn't allow the powder to fully molten. Then you have got this problem of lack of fusion, giving you some amount of porosity. And basically, you have to distinguish between these two types and play in between to get what is the good deposit. And of course, balling is another defect which can also is possible when your power is high, but you don't have enough time, provided that you can actually allow that to sink and deposit at the bottom of the powder bed, so that it can actually lead to cohesion with the rest of the solid. So there's a nice review by a building expert, Debroy, on these aspects, because quite a bit of our understanding is coming from the welding only. Okay, so you could look at that review for that. Now, here is a very nice paper, which I like it very much. It is also very recent, so this year itself. So where they have discovered a nice non-dimensional number using which you can actually predict what is the density you will get. That is how much of porosity you can eliminate. So this is something where, without having to go into the details of the microstructural formation, you can actually predict empirically what kind of a density you can get. Now we have verified this and we found that this is a very good measure. It is quite reasonable. However, it doesn't have the physics completely taken into account. So therefore, you can use it only as a one of the filters for your process parameter variation, but this is not the ultimate because it doesn't give you everything. But you can plug in and see where you are. So this is a data that has come from multiple alloys, and therefore it's fairly good, and it is available as an empirical correlation in the paper. Okay, and that empirical correlation is given here, and it does take into account the energy that is power input to the powder, E in. The E in itself is defined here. I have sort of, while making PDF, it has gone behind the text, but it is basically a combination of the parameters: power, velocity, height spacing, and layer thickness. Power divided by the three quantities: velocity, height spacing, and layer thickness. And that E is going into the calculations, which is a good idea that it takes into account some of the physics. So these can be used to eliminate the porosity formation as a first cut. And if you still have, then that means that there is something that we need to worry about, the consumable material, and that's where we have to do some more work. If your consumable is not having any problem of too much of adsorbed gas or something, then this correlation is fairly good to get you the kind of density that it predicts. Okay. Now there is another concept that has come in the literature again this year's paper, latest paper, on what is called the keyhole number. Okay, basically it is explaining. So it is explaining this particular diagram. Basically, this diagram is actually empirical. Originally, it is empirical. So this diagram has been explained in a phenomenological manner by using the keyhole formation, the likelihood of keyhole formation as a function of the parameters that are used for the laser. So you have got laser power, efficiency of absorption, the thermal diffusivity, the scan speed, and the beam radius. And therefore, these are all used to comment on how the keyhole formation can happen. And the keyhole number will tell the probability of that formation of the keyhole. And that if it forms, it means that you're likely to have the porosity due to that, basically. So So this is a very, I would say, nice outcome of decades of knowledge about keyhole formation in laser welding. So it's not come out of the blue. A lot of physics has gone into understanding keyhole over the last several decades, and today it is now coming of use because it is being applied to laser additive manufacturing to understand the porosity formation. Okay, so you can actually then what you could do is that you can have a scheme by which you can first initially do the thermal model, and then using those conditions, you can actually check the printable map, which is shown here, which is available empirically. You can calibrate some of the observations to know where are these transitions occurring. And once you have got, then you can use a single track to basically do those calibrations and ensure that these lines are available. And there must be some statistically meaningful calibration, because there are these powder distributions that are always having slight width. So if you have 30 micron powder, that doesn't mean everything is 30 micron. You know that it's a range of, let us say, 20 to 40 micron, for example. So therefore, certain variation is possible, and those variations, if you're able to take into account and then calibrate, then you do have fairly good ability to get tracks which are defect free. And then you can also go on to get the map and identify the condition, go on to print and then test it so that you can actually get the good properties. So there is a scheme of moving forward that is today possible, such that without too many experiments, with a limited set of calibration experiments, you can actually go on to do these. So the defect, understanding the defect, what you saw is very critical, because you need to know when you have the defects in your component, what type of a defect it is. That means where are we in this map, and therefore which way should I go towards the good printing conditions, and which means that which way I should vary the processing conditions. So that is the crux of it, and luckily the parameter space is well documented, and therefore the direction in which we can change is something that is quite easy for us to determine. Okay. Now the tracks are shown here as an example. So visually you can make out, when you make a track, a single track, whether the defect is balling track, a balling kind of a defect, or is it a lack of vision defect, or a keyholing defect, or is it a good track. So you can actually do the sections to understand which of the 4 regimes of the map we are operating in, and thereby we can actually calibrate our specific consumable and specific processing conditions with this map. And after that, we can operate in the region of safety, that is basically the white region, which is good printing region. Okay, so some suggestions based upon the trials which Hariharan has been doing in the last 1 year or so. So saying that, okay, if you wish, you can get some of the property data from TurboCalc database, because you can avoid having to go and do some serious ML, because all the properties are available from the thermodynamic database anyway. So you can use that, he says. And you can also do for individual alloys, but you cannot actually do it for across alloys, because you know that the properties of titanium alloys changes quite drastically when you go from, let us say, alpha alloys to alpha beta alloys to metastable beta alloys and so on, because individual alloying elements actually play a big role in the segregation behavior and the liquidus temperature and so on. So therefore, we have to apply these concepts only for specific alloys. Okay, and we must be able to realize that many of the things that we are talking about may not be applicable for reused powders, because the characteristics of the powder are changed in the reused powders, and therefore some of the things that we understand from the supplied consumable may not be applicable for recycled the powder. So there are certain such things that we need to still understand that are not universal. Okay. So I stop for the cracking, the porosity part here, and I need to talk about the cracking. So before that, I could also, I saw that I did not talk about the microstructure formation. So I will go there and show you some of that, because that's also something that is a very important for conceptual understanding. Okay, and then I go to the crack formation and I will wrap up. So we are halfway through now. So maybe I just pause for a few minutes. So you can ask me some question if you have, or how are you finding it? Any fundamental doubt that you have, you can ask me now. Srinivasan is there in the audience. Srinivasan, you have any question?
Yeah, participants, if you want, please write in a chat box also. I will take up the question.
Yeah. One of you have to read it out if there's anything on the chat box, because when I'm sharing the screen, the Zoom application shows me only a small portion of the window.
Yes, Professor. We can understand that.
Yeah, there is a first question. Yeah. Go ahead, Subbu.
Yeah, how to model the material property for simulation?
Okay, so normally, we don't have the material property readily available. So we have two possibilities. Both of them are being used in our group. The first possibility is identify which thermocalc or thermodynamic database is covering that particular alloy. For example, if you say titanium 6 aluminum 4 vanadium, that means it's a titanium alloy, and so we will look up the thermocalc titanium database, whether it contains the information for the vanadium and aluminum alloying elements, and of course it will contain, because titanium 6 aluminum 4 vanadium is a very popular alloy, and therefore we then can use the database to get properties of thermodynamic nature, like heat capacity, liquidus temperature, density, latent heat, and so on. Okay, so and then for some properties like thermal conductivity, then it's not a thermodynamic property, it's actually a transport property. So for that we will have to go to the variation of thermal conductivity as a function of compositions available in the open literature, and we can actually fit a regression type machine learning model so that we can estimate it for the alloy that we are interested. Now, because there is, you can make measurements of thermal conductivity by using laser flash setup. They are available in the market, so one can do. But usually it's a good idea to develop a machine learning model for unknown properties, so that you can actually extrapolate a little bit and verify. And once you have verified, then it is useful for you for further work. So that is the two strategies we have: looking up the thermodynamic database and building a machine learning model based upon literature data of similar alloys. So that is the two strategies we have.
Okay, thank you, Professor.
Yeah.
There is one more question. Yeah, how to design and develop the isotropic materials?
Okay, so that is maybe we should ask the person to speak, because it's not very clear what he meant by isotropic material. That is the how to remove anisotropy during building. Is that the question?
Yes, exactly, sir.
Okay. So the very first thing we have to acknowledge is that when we build, as you make the tracks, there is a anisotropy of properties along the track and perpendicular to the track. Okay, so that we accept. Now, if you want to avoid that anisotropy, you have to alternate the rastering pattern so that you have captured the rastering direction in all the directions of the 2D plane. So if you take, let us say, rastering pattern and change it like exactly 90 degrees, then you will repeat it within 3 layers. But if you rotate it by some arbitrary angle, like 37 degrees, for example, then by the time you come one full circle, the layer thickness would have been significant that it doesn't have any repetition, which means that you have basically captured all possible orientations of the rastering, and that's approximating to the isotropic behavior. So that is my suggestion. If you are interested in avoiding anisotropy of any kind of a build direction dependent properties, then have the rastering rotated at a very arbitrary angle, and then have the rastering also in checkerboard patterns, but the checkerboard pattern itself is rotated, then by and large, your component will be isotropic.
Okay, thank you, Professor.
Thank you, Professor.
Yeah. Any questions from participants? I think.
Okay, so let us move on. Let us
yes,
move on.
sir.
I will tell you some more concepts of microstructure formation so that you understand whenever you see the additively manufactured component, you can understand the microstructure slightly better, so you can imagine what more is going in there. Okay, so so here is one concept called interface response function. Now, in few months from now, we will be releasing a program which will let you calculate it. So don't worry about the theoretical complications. But I want to tell you that the metallurgical knowledge of what is the interface temperature during the solidification as a function of the initial composition, then partition coefficient, the gradient of temperature in the solid, the gradient of temperature in the liquid, the velocity of the interface, the radius of the dendrite tip, and so on, all that can be actually modeled today through analytical modeling. Now, the only difference that occurs between casting and additive manufacturing is that in additive manufacturing, you always have a build plate. So there is always an initial solid, which is actually growing into the liquid pool, and therefore the thermal undercooling can be neglected. So that's the one difference with the model, but the remaining things are all applicable, and therefore one can use the casting literature or welding literature to apply to the additive manufacturing. So what do we mean by the interface response function is the interface temperature. Now, why is it important will be evident in a moment. Now, you see that when there is a segregation of elements, as you have seen the dendrite formation, and between dendrites, there is an enrichment of solute. What happens is that enriched solute, when you combine with the liquid slope, will give you the undercooling or driving force. This kind of a driving force is called as the solute undercooling or solutal or hypercooling. Okay, solutal hypercooling or solutal undercooling. Now, that's a driving force for solidification, and that is one of the many type of driving forces. Now, the next driving force comes from the curvature of that dendrite tip. You have seen in the videos I have shown the dendrite is like a tree shape. So the curved nature of it will also give you some driving force. And the H here is basically the averaged curvature. It is called the trace of the curvature tensor, and gamma is the surface tension. This is the molar volume of the solid phase, and delta S is the entropy of diffusion. Okay, Tm is the melting point, and this is the temperature of equilibrium between the dendrite, curved dendrite, and liquid. So what I want to just convey here is that if you have a dendrite that is very fine, then there is more driving force, and if the dendrite is very fat, then it has less driving force for solidification. That's what you can convey from here. Okay. Now, this term is something that you know is real, because here we have experiments that are shown to show that the melting point of gold or aluminum can actually be reduced significantly if the particles are nano gold. Okay, nano gold here or nano aluminum. So that is a direct evidence that what we are talking about is physically realistic. So if somebody asks what is melting point of gold, first question you ask is what gold, bulk gold or nano gold? Because if it is nano, the temperature of melting point is reduced by almost 300 Kelvin. Okay, the reason it happens is because of this term, the melting point is reduced by that much value. So if it is nano, then this being a curvature, it will be 1 by R. So therefore, this value will be high, and therefore the reduction of the melting point is large, and that reduction of melting point is nothing but driving force. Now, the driving force is then combined with the surface energy, which is anisotropic, and together will then lead to various pattern formations such as these facets. Facet means sharp faces. Sharp faces are bad news. They are not desirable. And what kind of phases will have sharp faces? Like, for example, the intermetallic compounds, particularly the detrimental fellows, they usually have sharp facets, and we don't want them because they are detrimental, and the sharp face also means that the crack can move between the intermetallic compound and the matrix a bit fast, and therefore they are actually double whammy. Now, the last undercooling is because of the velocity of the laser being very high. That's called the kinetic undercooling. So here is the velocity of the laser or heat source or velocity of growth. And this is the kinetic coefficient. That's also anisotropic. So a combination of all these terms is what gives you the interface temperature. So the interface temperature is not the melting point. It is reduced by a certain magnitude because of the surface tension effects, because of the composition effects, as well as because of the kinetic effects. Now, all those things will actually lead to the morphology changes. The kinetic coefficient itself, this mu, can be kinetic coefficient, can be also available, which is different in different materials. It can be anisotropic to show you that a crystal that is growing can be a beautiful dendrite like this, or it can be like a ball, which is isotropic. So anisotropic growth or isotropic growth are both possible given a material if there is an anisotropy of the kinetic attachment coefficient. Now, there are models available for this. We have done that work, and we can simulate the growth of the solids in a molecular dynamics framework and determine some of these coefficients. That was done by Ramakrishnan during his PhD, and we have found which plane and which direction actually are having less energy, for example, interface energy, and what is the magnitude of difference with respect to the faster and slower phases, for example. So those can be documented from molecular dynamics runs, and they will be directly affecting the morphology formation. Okay, so all those are inputs from molecular dynamics into the mu. The diffusion field can be solved, and that will go to the C. The thermophysical data is available that will give you the surface energy, and the velocity of the laser torch also can be giving you the V here. So in other words, all of these can be calculated, and you can find out what is the TI, and that is nothing but the interface response function. And that, when combined with the process parameters like velocity, can give you a lot of information about the driving force for solidification. So here is some map like that. As you increase the velocity in the x-axis, the interface temperature is on the y-axis. And the thumb rule that I want to tell you is that whichever curve has a higher value, that is the kind of morphology that is to be found. So here you can see that the morphology of cells and dendrites is higher here. So that will be found for intermediate velocities. And the planar morphology has curve here. So the planar morphology will be found. So whichever is higher will be the one that will be formed. Okay. Now here is a place where there's a competition between two different phases. The black curve is the interface response function for beta phase, and the red curve is the interface response function for alpha phase in a titanium aluminum alloy. And as I told you, the upper envelope gives you the which phase will form. So which means that at lower velocities, alpha will form, at intermediate velocities, beta will form, and at very high velocities, again, alpha will form. Now that kind of information of phase selection is possible once we are able to model the interface response function. Now this program to calculate this is being made ready by Hariharan as part of his PhD, and it will be used in conjunction with additive manufacturing, because in additive manufacturing, we are on the right-hand side of this particular plot. So we are on the right-hand side. So there's a phase selection that is possible here. So we can capture it to actually understand which phase is forming at what velocities. That way we can actually control the microstructure also. Particularly titanium aluminum alloys is very important, because you may want to play with it to get a specific phase to solidify upon printing. Okay, and once you have that information, you can go on to actually change the gradient for which you have done the calculation, and then perform the calculations for every gradient, and thereby you can actually make a microstructural map. So that is very powerful idea, because what we mean by microstructural map is, if you tell me the alloy composition and at what gradient and velocity you were doing the printing, I will tell you what phase will be there and what microstructure will be there. Now that's almost like a prediction that is possible, and this technology is not very new. You can see that this paper is about 2005. The concept of microstructure map is dating back to 1994 from Kurz. So you can almost say that 25 years back itself, this concept was known. But in additive manufacturing, today we are exploring the right-hand side of the domain here very comfortably because lasers can move quite fast, or even electron beam can move even faster because it has higher power. So one can actually explore the microstructural maps much more robustly today and take advantage of that information to make a printed component of any phase in microstructure as we desire. Okay, so that is something that is powerful idea today. Okay, and one information that is also going to come in conjunction with what we have discussed is that the velocity and the interface temperature is related to the undercooling, because as you can see here, undercooling is nothing but the Tm minus Ti. Okay, so difference between these two is undercooling. So that can be used as one of the parameters on the x-axis, and velocity can be the y-axis, and they can be correlated experimentally. Once you know them, you can make simulations of how the microstructure will form. So this map is something that I want you to relate with what you have seen in the video in the beginning of the lecture. I have shown you that you can have cellular microstructure growing, and you can also have nucleation of grains in the front, which will actually settle down and form equiaxed growth. So there is a competition between the columnar growth and equiaxed growth. And one important parameter for the competition is the velocity with which it can grow. Now that velocity is mapped with the undercooling in this manner. So this is basically coming as an outcome of the interface response function. So today there is a mathematical way of describing that, and that is available with us. And once you put that in, what happens is that you can actually make some calibration of the number of nucleation events that can take place, and then start to simulate microstructure and the grain formation. So you can actually simulate in the computer how much columnar growth is possible and how much equiaxed growth is possible. So now that is a reality today. And today we have simulations that are possible to do this in a very easy manner. Now you can also use those same concepts to relate to microstructural simulations. As I mentioned to you, the phase field simulations can be done, and you can combine them to have the predictions of the segregation patterns, and these can be related to additive manufacturing quite easily, because the difference between casting or solidification welds versus additive manufacturing is only in terms of velocity. Okay, so today if you see microstructures of that type, the segregations, etc., then all that is today very amenable to calculating. It's not something that you need to worry about in experiments. You can calculate them and have them under control, the segregation levels, etc. Okay, so I stop here for the segregation part, and then I go back. Last topic for me would be the cracking. Okay, so the crack formation during the welds. So we have seen the property, we have seen the porosity, but cracking alone we will see now. Now, the cracking phenomenon is a very extensive topic. There are multiple volumes of weld cracking that are available, and there's a nice review of it by Eskin in Progress in Material Science. It's a fairly large paper, so I recommend you to read it whenever you encounter cracking in any of the built components. Of course, this paper is not on additive manufacturing cracking, but additive manufacturing cracking is no different from the weld cracking that people see, because the weld overlay is exactly same as what you do as a track in additive manufacturing, and therefore the same concepts will apply. Okay, except the size. Size is a bit small in additive, but the same concept will occur. Now, whenever we talk about cracking, so there are some names that are used by people. So they talk about what's called solidification cracking. Okay, just a moment. Ponnarasan has done a question. I will come to that in a moment. Okay, let me just finish this and I'll come to you. So there are some names that are used by people in cracking. So they talk about strain edge cracking, they talk about liquefaction cracking, and they talk about solidification cracking. Sometimes they use the words like hot cracking and hot tear. So are these very different? Are these same? I mean, this is something that one should know. So here I want to tell you very clearly, solidification cracking, hot cracking, and hot tear are same. Okay, they are the same concept. And liquefaction cracking is a bit different, because liquefaction cracking is occurring because of a eutectic that is melting upon reheating. Okay, so during solidification it is occurring, then it's a solidification cracking or hot cracking. But during reheating, if it is occurring, because a eutectic region has molten, That's called liquefaction cracking. Now, strainage cracking is a totally different concept. Strainage cracking is when you are trying to homogenize the material, you want to remove the concentration gradients in the material and you are keeping it at a high temperature and waiting for some time. Then during the homogenization process, the segregation can actually lead to cracks because the diffusivity of species is different in different elements. So because of that, you may actually have a void nucleation and then crack formation. And therefore, that's actually strainage cracking. So strainage cracking has nothing to do with, let us say, solidification cracking. Okay, so they're very different concepts. But unfortunately, in the case of superalloys, nickel-based superalloys, you will have all three of them present. Okay, so you can have and if your luck is like that, then you will have all three possible cracks. And you must understand how to eliminate one after other in a very careful manner. So in a printed component, you can avoid all of them if you are very careful in the choice of processing conditions and also to minimize the homogenization treatment. Okay, so that is some direction of research these days. So in that context, I want you to note down that there is a map of the titanium and aluminum contents for nickel-based superalloys by Henderson, which actually tells you whether or not an alloy is crackable, weldable, because it has a cracking or not. Okay, so you can see that there is a space, the domain between the alloy elements is split to show you that certain alloys have inherent cracking possibility and certain alloys are weldable. By weldable, we mean they don't have cracking upon welding. It's the same thing as they don't crack upon printing. Okay, so almost the same. Okay. So how do those cracks look like? Solidification cracks. So they can be quite, serious in the sense that the material has such a big crack that you simply cannot heal it and you can't use the component. The component has to be thrown. Now, if you know the cost of a printing of a component, you know that it can run from about $1,000 to $2,000 sometimes, depending upon the size. And if you have to throw it, it's because there's a big crack. That's quite sad. So we must understand this phenomenon quite carefully and avoid having that in our printing. Now, if you go back and look at liquefaction cracking, the location of liquefaction cracks are slightly different. They will show you the eutectic formation nearby, and therefore you can make out that, yeah, there is a liquefaction that has happened. Okay, there's a eutectic that has actually formed liquid during heating, and then that liquid has gone around and created a crack. So that is something that you can make out. Okay, and that liquefaction cracking of because of eutectic formation and eutectic molten can happen also because some of the carbides can form eutectic with the matrix. So whenever you have got carbides in superalloys which are chunky, then you can have a eutectic between them, and then that's what it can actually also cause the liquefaction. So one has to be very wary. You may want the precipitates because you want the strength, but eventually that also should not lead to these problems. Okay, so the reheat can actually do those kind of formation. So if you have niobium carbide, for example, you will have this weld heating leading to basically a liquid formation, forming a crack, and then you will have a problem. So here is where actually you should relate these things back to what I was talking in the first 1 hour, namely the segregation of niobium. Okay, so if you have any segregation, then you will see that some of these possibilities of eutectic formation or compositions that are approaching a lower liquidus temperature kind of a regimes are very much possible, and therefore we should eliminate such possibilities and avoid serious segregation levels from taking place. So that's one of the reasons why we have to understand segregations. Otherwise, it's not as if we have a design and we can just print it. Okay, so only when the print cracks, then we understand how bad the situation is, and unless we solve it, we can't actually go on to print one more component as a trial and error, because each trial is actually very expensive. Hot cracks, how do they look like? If you take a bead of weld, it looks like the entire bead has broken in the middle. Okay, so it can be quite severe in that sense. So some understanding of cracks is important for you because these are the same concepts as in additive manufacturing. So I'm going to mention that to you. So the hot cracking or solidification cracking or hot tear occurs towards the final stage of solidification, so towards the end of solidification. And it is also called as the hot tear or central line cracking in the weld, but it's called as just hot cracking in the case of additive manufacturing. And it actually occurs because the stresses are generated due to volumetric shrinkage, and then there is a thermal contraction, and that's what is leading to this crack formation. Okay, so this is actually related in the case of weld with respect to the fixturing as well as the welding parameters. In the case of 3D printing, the thermal cycle is quite well established. So you can think of the weld parameters as replaced with the printing parameters. The weld fixturing can be replaced with the geometry of the printed component, and the alloy composition with respect to the powder composition. So all three can be mapped over to the printing, but the physics of hot cracking remains the same. It's the same problem that is going to occur also in the superalloys when you don't take care. Are there examples of alloys which will surely crack if you just try to print again? So CMSX4, for example, is a superalloy, and it's a very important alloy. And if you don't take care, if you print it, sure enough, it will actually crack. So you have to take care of cracks in some highly crack prone alloys like CMSX4. So what are the various factors that affect the cracking tendencies? So there are metallurgical factors as well as mechanical factors. Okay, so metallurgical factors are about the material properties such as the solidification range, that is the temperature of solidus and liquidus, and dendrite coherency. That by that we mean how closely are the dendrites with each other during the solidification, so that they can actually form bridges with each other, for example. Eutectic fraction, that is basically telling you how much of liquid is available in the last stage of solidification, so that it can go and fill the regions in between the dendrites and make the solid compact and not have any gap in between, like a void, which is basically a crack. Backfilling, that is the ability of the liquid to flow between the two grains or two dendrites so that it can fill it. Sometimes it doesn't happen because of a intermetallic formation that is preventing the black filling from happening. And then surface tension, because if it has wetting problems, then you have that issue also. But of course, in superalloys, that's not a very serious issue. Sometimes grain boundaries also play a role. If you have many small grain boundaries, it is good. So fine microstructure is good when you want to avoid these hot crackings. But if you have coarse grains and that too with the texture, then it could be a problem when it comes to cracking problem of solidification origin. And of course, porosity. Okay, so that also can play a role. So mechanical factors like strain, stress, and then the rate at which your strain is changing, which is dependent upon the cooling rate of the printing, and of course the restraint, which depends upon the geometry of the component being printed. So all of them will occur. Okay, so there are various theories that are available. So I will go through some of them. So one of the theories, celebrated theories, is by Lippold. And I will not go through all of them. I just mentioned that there are some names you must have heard of. That's why I'm mentioning these names. So Prokhorov's name is very popular in cracking, because anybody who's talking about hot cracking should have mentioned about Prokhorov's model, because he was one of the first successful models to explain the cracking tendencies. And that he is actually said that by looking at the strain as a function of temperature, and then whether it exceeds a critical value or not, and then comment upon crack formation or not, respectively. Now, strain rate based models are more successful compared to strain based or stress based. Okay, so strain rate based are today the most popular. And if you have heard of models like RDG model or Sindokov model, they are basically coming from the strain rate based models as a starting point. Okay, so I will skip the strength-based models. Okay, and I go to the strain rate-based models. Okay, yeah. So the most, as I told you, the first major successful attempt for the explaining this hot cracking was by Prokhorov. And then there is a very celebrated criterion. Everybody should hear about it, the so-called RAPA criterion, okay, RDG criterion, that explains why cracks form in any solidification process. So he has explained it so beautifully that it is applicable for casting, welding, and additive manufacturing. So it's applicable in all problems where solidification takes place. And Sindokov has simplified that particular paper by taking a small portion of that particular analysis to give a gradation of alloys which will crack more and which will crack less. And that kind of a gradation by what is called the cracking susceptibility was very useful because it will let you grade one alloy as more crack prone than another alloy, which is very useful to know. However, it doesn't help you in identifying conditions under which crack-free solidification can take place. That's a limitation of the Gauss criteria. Okay. The Prokhorov BTR concept says that there is basically a temperature range where the ductility actually is not available, and therefore the shrinkage cannot continue at a rate that you are doing, and then it will crack. Okay, so that kind of a measurements are now possible in Glebel, and therefore Prokhorov's BTR concept can be expanded to Glebel tests today, and we can characterize the crack susceptibility quite well by experimental measurements itself. Okay, and if you look at the origins of the RG criteria, they are all talking about how the liquid that is trying to feed the solidifying region is suddenly getting its channel cut off. So that kind of bridging leading to the channel being cut off as the reason why the crack actually can nucleate, because all metallic materials with the exception of bismuth will shrink upon solidification. So if this much of volume of liquid has to shrink, then the liquid has to come from outside to fill the gap, and if it cannot come because of bridging that has happened, that means that there's a likelihood of a crack formation. So that is a kind of an idea that is actually overbearing in this concept. And then one can actually go on to see microstructure effects on how to prevent cracking. And eutectic fraction of alloys is very important, because if you have some eutectic in the alloy towards the solidification completion, it helps because that eutectic actually solidifies at a slightly lower temperature compared to the rest of the alloy. So it is available as a liquid, and it will go and fill the gaps and therefore sort of heals the cracks and therefore prevents the crack formation. So one solution for any alloy which is actually having a cracking problem is try to find if you can move the alloy composition closer to the eutectic in that particular alloy. Okay, so eutectic means that it is easily solidifiable or castable, and therefore eutectic compositions are the best when it comes to avoiding the cracks. Of course, you cannot always choose eutectic alloys, so at least you can have a eutectic liquid that is present in the alloy, which will help you in reducing the crack susceptibility. Okay, so the physics of it, how it is happening is here. So if you take the solute availability, what happens is that the liquid that is able to move in between the grains of the solid can actually go on and heal the cracks, and if it doesn't, then there's a problem. Okay, and of course, if you have got equiaxed grains, there is no problem at all, because there is no channel that can be cut off. The liquids all around the grains, and therefore that will be very least susceptible to cracking. So equiaxed microstructures of fine grain size are least susceptible to cracking, whereas columnar grains, which are very long and in the direction towards making a single crystal printing, would be actually highly susceptible to cracking, because they may actually prevent the liquid from reaching the channels, because there may be bridging that can happen here, and then the channel is cut off. So columnar growth, more susceptible to cracking. Equiaxed growth, less susceptible to cracking. Okay. Now, the freezing range also will give a hint about the cracking susceptibility. So for any alloy content, if you have freezing range, for example, in the case of aluminum copper alloy, so you know that around 4% of alloy copper content is the freezing range is maximum, and that's also the alloy for which the crack length is maximum. So again, you can draw a thumb line, that is a thumb rule, that is, if the freezing range of the alloy is more, that is, if the difference between the solidus and liquidus temperatures is more, then the crack susceptibility is more. Okay, just straightforward thumb rule we can draw. Okay. And how does the surface tension affect? That also can be understood as the way by which the liquid can wet and go on to fill the gaps. And that is also helping in which alloys actually can have less susceptibility for cracks. Okay, so I move on to show you the physics of it here. So you can see the dendrites that are growing and how the bridging is happening between the dendrites, and how the last to solidify liquid are available as islands, and how some of them may lead to porosity. Now, if the porosity or cracks are going to occur, it is very good idea to have them as distributed over a long distance, so rather than a one continuous segment, because a continuous occurrence of a porosity is same as a crack. So which means that if at all you are going to end up with this kind of a dendritic growth, one thing you should do is ensure that there are so many bridges that the liquid packets are actually distributed along the length, very broken in their, not connected at all, which means that a fine microstructure of the dendrite actually will help you. Now, fine microstructure of a dendrite is more likely when you have a higher speed. So which actually also experimentally also observed that if you have slightly higher speed, then the solidification cracks in aluminum alloys have been avoided. So that is our practical experience we have seen. So that way what happens is that the microstructure starts to play a role in the crack avoidance. Now, how does that relate to printing? It's very simple. If you have a cracking problem in an alloy where the microstructure happens to be dendritic, then try going a slightly faster with respect to the laser scanning speed so that your microstructure is slightly finer, and maybe you will have a lesser cracking problem. Okay, so that is a direction, thumb rule we can try to use. Okay, so this is how the physics is imagined, that the liquid is in between the dendrites and that is trying to shrink, and the rate at which it will shrink because of solidification as well as the thermal contraction should be matched with the rate at which the liquid is entering the region. And if there's any mismatch between the two, then you have a crack formation. So that is the idea of how the mathematics has been evolved. And with that, the criterion has been made. The criterion shows you that the alloy composition where the freezing range is high also has high susceptibility. So which also means that when you choose an alloy for printing, make sure that the alloy has less freezing range if you have a choice for it, or it has at least a eutectic formation towards the end of solidification. So that way, at least you can avoid the crack formation. So microstructural assumptions are made in Synthocow's criterion, which lead to its limited applicability. And we have addressed some of it in our studies recently to avoid the limitations of the Synthocow criteria, which is very only, it's like a gradation of alloys which is cracking only, but we can also predict the crack-free processing regimes using this. So here is where you have got the equation. So here you can see that the rate at which the strain is changing with respect to the temperature, if it is larger than certain terms, one of them is how the liquid fraction or solid fraction is changing with temperature. And then the second term, it has a cooling rate. Okay, and this has to be evaluated. This equation has to be evaluated in the limiting condition of towards the end of solidification. So from this equation, what we can say is, if you have this particular term very low, that means that the right hand side is low, and therefore the left hand side is likely to be higher. Okay, or you can also do one thing, the cooling rate you can play with it. The cooling rate is slightly higher, then because it is coming in the denominator, then this term will become smaller, and that also will help you. So either you make the phase diagram of either you choose the alloy such that the last to solidify solid is over a small range of temperature, or you have a slightly higher cooling rate. They both give you the same effect. Now, this is a very good clue for us because Synthocov used only the first term to grade the alloys, and he neglected the second term, which has come from the Rappa criteria. What we have done is we looked at the second term also and shown that in situations where there's a cracking possibility because this part is already bad, then you can improve here so that you can put slightly higher cooling rate and therefore manage to keep this particular right-hand side term low, small, so that you can actually go on to actually ensure that the separation doesn't take place. Now that has been done and we have verified it with some alloys also. So which is a takeaway for the additive manufacturing community, that is, whenever there's a cracking and you don't have a choice of changing the powder, then what you can change is the scanning speed. So you can change the scanning speed and see whether you are able to increase it to a level that you can avoid cracking. But of course, you cannot randomly keep on increasing it, because you know that if you increase beyond some value, then you will have lack of fusion taking place and you will have other kind of defects like porosity, which we have discussed earlier. Okay, so with that, I stop here, and I have one last set of slides about the ICMA approach. With that, I will close, but I may want to answer some questions from you. Let me just open and keep it ready. Okay, so Ponnarasan has a question. He's asking, buoyancy forces can change the microstructural properties in formation. I would say the buoyancy convection in additive manufacturing is negligible, because the convection within the melt pool due to buoyancy is in the order of less than 1 millimeter per second, whereas the convection in the melt pool due to Marangoni convection is more than 1 meter per second, and therefore Marangoni convection is more dominant. Buoyancy convection is negligible. Okay, so don't worry about buoyancy when it comes to laser-based additive manufacturing. It doesn't affect. Bharat Krishnan is asking, in TIE 6.4, due to rapid cooling after printing, martensite structure is formed. Does diffusion-less phase transformation take more chances of cracking? So you have two issues here. If you have martensite formation in alloys where the martensite phase formation is possible, because there is a phase that is transforming, and what you can do is have the two-phase microstructure to absorb some of the strain that is caused due to the martensite transformation. Okay, that's the only way you can avoid the cracking formation. If you don't take care of that, then definitely the volumetric change, the molar volume change during the martensite transformation will cause strain accumulation, and it will cause cracking. Now, this is a well understood concept in metallurgy. So those of us we have been doing in steels, we know that if you have high carbon steels and if you do rapid quenching after heat treatment, they will crack. But what we do is that we will quench slowly and we will do tempering, and therefore we avoid cracking because we are managing the strain caused due to the large amount of carbon that has gone into the lattice when martensite is forming. The same concept can be applied to any two-phase regions, like even in titanium alloys and duplex stainless steels, etc. You can manage it by ensuring that the phase to absorb the strain is available as a part of your microstructure upon printing. So which means that you have to print with conditions that will have that phase fractions possible, which means you have to take care of the phase evolution during printing. Okay. Syed Khadir is asking, how does the solidification take place in case of multi-material additive manufacturing? So if you have a multi-material, as in multiple powders are mixed, then actually in the path of the laser, the alloy powders, all the powders will actually melt, and you can assume it to be almost like a multi-component solidification only. Okay, so that is possible, and most probably it is valid. Where you don't have it as a valid is as follows. If you have high melting point powders, like for example, let us say you have got some titanium and tungsten powder along with aluminum powder, and you are trying to deposit, what will happen is that the laser heat source will be adjusted to ensure that there is not too much of melting of the base material, which is aluminum, and therefore it doesn't melt the tungsten powder fully, and therefore the tungsten powder unmolten is then coming in contact with the liquid melt pool, and then it will start moving around mixing. So you will have inhomogeneity of alloy content within the melt pool. Okay, now you can tune it in such a way that it can be for your advantage actually, but in many situations it's a problem because your melt is not a homogeneous melt. Okay, so it's a problem. So you have to ensure that the melting points of the powders that you are mixing are not too away from each other. Okay, and the heat source is strong enough that actually the molten powders are fully molten, so that they can mix before they come in contact with the base plate. The solution for it is basically by taking the alloy powders than pure metal powders. Okay, so that's a best way to do. Okay, so alloy powder is always a better idea whenever you have multi-material printing. Okay, so last set of slides, just 5 minutes or 10 minutes to tell you the latest work in my group about the ICME approach. This is to show you the direction in which the work is going on in these days in our group. So if you look at the laser additive manufacturing, you will have problems like this: printing, cracks of printing, and samples coming off from the base plate with cracks going through the component. So they're all attributed to residual stress. And today we have software such as Simufact Additive, which allow you to calculate those residual stresses. And they can take into account the thermal stresses, thermal strains, and phase transmission strains, and so on. So elastic, plastic, thermal, and phase transmission, all the strains can be taken into account. And we can then go on to quantify the residual stress in any component using the X-ray diffraction technique. And we can also do other techniques like hole drilling or whatever. But X-ray diffraction technique is the most commonly used. So why we do it is because we want to then bring the residual stress to a very small value so that there is no accumulation of residual stress as the component is being built, so that the component doesn't crack in the end. Okay. So we look at all the parameters and see which parameter affect the residual stress which way, because theoretically it can be done. And then that will give us a hint on how to basically play with the processing conditions during printing so that the residual stress is under control. So the arrows will show you which way the residual stress is affected when you change that particular parameter. Okay. And you can also bring the residual stress under control by having a scanning strategy. So the rastering can be changed in such a way that the residual stress is not accumulated in the plane and then plane by plane, etc. So that is also something that can be done, and you can play with it by computer before you go on to build. And you could also play with the thickness of the layer, and we have also done some studies to show how the layer thickness, individual layer thickness, can also play a role in the accumulation of residual stress. And of course, if you don't have the residual stress under control, what would happen is that the choice of energy parameters also can start to aggravate a lot. Okay, so you have these defects that we have talked about earlier in the context of porosity. They will actually be much more aggravated if your residual stresses are slightly high. Okay. So maybe I just show you one last. So these are some works that we are doing about the ICME approach. I should close now. Okay. So last two slides, I show you the cracking susceptibility today in additive manufacturing. We are able to predict it by computational methods, and we are developing an integrated approach of many tools so that we can attack the 3D printing problem, understanding as many features of the physics as possible through computation. So all the tools that you are seeing on the screen now are computational. So today we can actually do the computationally optimization before we go to the printer, so that in 1 or 2 iterations, we get the best component from the printing. In fact, we have demonstrated it already by making a very good component in the very first iteration when we worked with Professor Keshavan's group on Haynes 282 alloy, and we have already submitted one manuscript for that recently. So today we have this ICME approach that is possible, integrated approach to combine all the scales from the component to the multiple to the microstructure and down to whatever is happening at the atomic and molecular scale also. And therefore we can actually build defect-free components by understanding thoroughly. I encourage all of you to not ignore the metallurgical aspects I have talked to you in the last 2 hours, and ensure that whenever there's a problem with microstructure or residual stress or cracking or defects, etc., please go in depth into the formation of those for that particular alloy. There are solutions available for it from the welding community and casting community, so we can bring that knowledge across and accelerate the development of the additive manufacturing field to make defect-free components for our end user. So maybe at this point I stop. I will close my presentation and let you ask some questions. We have about another 10 minutes of time, so we can do that. So maybe I should say stop share. Okay. So if you have any questions based upon what we have discussed, you can ask me. I have tried to cover as much of metallurgy that is possible to explain both microstructure formation as well as defect formation. It could be perhaps a little more material to absorb, but I want to also give you confidence that there is a lot that we know about these things. So, I want to also give that sense across, because many people assume that 3D manufacturing, 3D printing is like, you have a design and you print a part and there's nothing else to do. It's far from that. There's so much still to do. Thank you. So Keshavan, thank you for the opportunity.
Yeah. So thank you, Professor, for the very detailed presentation, which is very enlightened talk. And I would really say that it's a very rich and informative presentation. I believe most of the researchers, research scholars, they will look into these aspects. So they may not get the opportunity to see the metal 3D printing in this direction. So on behalf of the organizing committee and the institute, we thank you, for enlighten on these areas. So if an audience, and if you have any questions, please either you unmute and ask your question, or you can put those questions in the chat window.
I'm also assuming that other speakers till now have not gone into this aspect of the subject.
No,
so I hope it was not
that's true. So all the information, so what you have given today, so they all actually new. So
okay. That's good.
Yes. And of course, as you mentioned, a lot of scope for researchers to work on these areas. So yes. So I mean, it's not that only metallurgy people with only metallurgy background can work on this. Even with mechanical background, with a little bit thermal knowledge, they'll be able to get into these areas.
Yes. No, in fact, the other way, I would say this area belongs to mechanical engineers,
Yes.
and metallurgy also is important, is what I'm saying.
Yes. But we don't see much mechanical researchers work on these. So,
I think we should join hands.
Yes.
That's the best.
That's where actually we started. Maybe actually we can, going forward, we can actually do a lot more on this, sir. So
audience, please don't worry. You can ask any question. We have another 5 minutes, so feel free. Ask any question.
Sir, this is Syed.
Syed, go ahead.
Yeah, sir. Actually, regarding when I'm going for this nickel titanium powder for shape memory alloy printing of 3D manufacturing. So what happens is, I was going through the literature. So what I got to know is that nickel is mixing with titanium particles before itself and forming nickel titanium 2.
Okay.
NiTi2 particles, which are very brittle in nature and causing defects in the component. So when we are doing with laser, in case of pre-mixing, if you are going with pre-mixing, so what can be done? Like many people have come up with different hoopers for different, and then they are mixing it together.
So here, the way I would proceed is, we can theoretically calculate the so-called interface response function for the two phases that are important, the detrimental phase and the phase that you want, and see at what velocity you can actually avoid the phase, which was forming in the beginning. And you can actually see whether or not it's possible. For example, I'll give you the example of neodymium iron boron. In the case of neodymium iron boron, initially people thought we can get the hard magnetic phase directly, but when we did the theoretical calculations, we found that it is impossible. So once we know it is impossible, what they did is they went through the rapid solidification route. Then they made ribbons and they made powder, and then with that they made the hard magnets, and that's how they worked around. So same way for nickel titanium system also, if we can do the theoretical calculation, we can see whether there's a possibility of the phase that you want to form from the liquid. If it is possible, then we can explore that window and go on to use it. If it is not possible theoretically, then there's no point trying it. Then we should find alternate ways of getting that phase through as I told you, there are examples from other systems that people have looked at.
So people have overcome this through with CWW, cable wire welding.
Yeah.
So they are twinning it and they are doing it. So 1 or 2 papers I found like that because of this defect.
Yeah, so that's why I said that the pre-alloyed powder, which is rapidly solidified so that it contains only the composition as well as the phase that you want, is always preferable because it avoids the mixing issues and new phases formation during the printing. And so which means that your initial consumable is also a question. And surely there is a difference between a wire consumable and a powder consumable.
Yeah.
So there could be situations where a powder consumable cannot give you what a wire consumable can give you. It is possible. It is possible.
Yeah. And this is very basic question, sir. So when laser falls on the powder material, so the laser will have some sort of arc pressure.
Yeah.
Where material will flow away, or it will fly away. The amount which we are thinking of a layer height, or so this arc pressure will move away the particles, and to a certain extent, how that how it is happening at that junction.
Yes. Yeah, it does. I mean, we see it visually also. So the arc pressure is there, and but what happens is in a directed energy deposition, you already lose almost half of the powder because of the carrier gas. So if the powder is moving away because of the arc pressure, it's one of the many effects that the powder is going away. In the case of a powder bed, what is happening is that because there is a bed all through, and there is always the melt pool, which is by surface tension trying to hold the remaining powder that is being molten down, there is a chance that there's more material that will be actually deposited, slightly more efficient in terms of the powder that is being wasted, slightly more efficient. And but otherwise you can't actually help. Arc pressure, nothing we can do about it. Sometimes the morphology of powder may minimize, but we don't play with the morphology because it affects us in the flowability. Okay, because morphology of the powder is important for flowing the material to make the layer every layer by layer. So we don't touch that thing, so we don't optimize that.
Okay. Thank you, sir. Thank you so much.
Maybe one more last question from the audience. We're almost reaching the end.
Hello, sir.
Yes.
Sir, this is Jipin from IIT Palakkad.
Yes.
Sir, it was a very nice presentation, which gave a detailed overview of concepts in metallurgy. So, sir, my question is which is the best method to measure the residual stress? You commented HRD is one of the method most of the people are going for. So, or what is the trustability of that?
I would say theoretically the best method is neutron diffraction. Okay, because neutron diffraction will measure throughout the component, but neutron diffraction is available only when you have a nuclear reactor nearby, and therefore it's very difficult. So if you have collaboration with the BARC or some nuclear plant, you can do that. But I would say practically it's not easy. So let us forget that. The second best is X-ray diffraction, and X-ray diffraction is what is a trusted trusted method for non-destructive evaluation of residual stress by all aircraft companies. Okay, so therefore you can say that X-ray diffraction it is. Okay, that's what it is. Okay, that's the most recommended. Now, if you come down, indentation-based techniques are also possible, but they are not non-destructive because you always leave the indentation behind. And then if you come down further, even more destructive will be a hole drilling method. Okay, and there are also methods like you can have a particular geometry so that you can measure the overall distortion, and from there you can calculate what would be the residual stress. But they are all destructive. Non-destructive and highly believed by people is X-ray diffraction.
Okay. Thank you, sir. Thank you very much.
Sir, one question from the audience from Dr. Jesse. In what way we can study defects in parts manufactured using fused deposition printer?
in what way we can study defects. So the very first thing is, if you have internal defects, then you will have some requirement of a CT scan. If it is a thin component, and if it was thick component, you will have to look at whether radiography was relevant. If it was surface or closer to the surface, and if the material is magnetic, you may use the standard NDT techniques to study what are the defects. And if it was exactly on the surface, then you always have a surface profile meters to understand how much of surface defects are possible. One thing we have to remember is that we have to locate which part of the component is critical for the application and ensure that the defects don't occur there, because it's impossible perhaps sometimes to avoid defects completely. It's only better to sort of localize it in a place where it is not dangerous. That may be a more practical solution.
Okay, so we are almost come to an end.
Yeah. So we should
thank
move
you.
on.
Thank you for again.
Okay, good to see you.
On microstructure.
Good to see you after some time.
Yes, nice. So
okay.
All right. Thank
We'll
you,
on.
Professor. Yes.
Yeah. Okay.
Thank you, Professor.
Welcome.
Yes, sir.